Hey, what's up? I'm Ryan Hay, and in this video, I'm going to show you how to install an OpenShift 4.5 cluster in a bare metal environment using the UPI method of installation. So that's user provisioned infrastructure. And what that means is that the user is responsible for provisioning and maintaining the infrastructure that the platform runs on. Now this is a little different to the IPI method that's also available. That's installer provisioned infrastructure. And that's available in public clouds and also some on-prem stacks like OpenStack and vSphere. The IPI installer will automatically provision and maintain the infrastructure for you. So for the most part, if you're in an environment that's supported by the IPI installer, you probably want to use that method. It's a lot simpler. If you are in an environment that is not supported by IPI, however, you'll have to fall back on the user provisioned infrastructure method. There's two requirements to follow along with this video. First of all, you need access to 7 different machines. For this, I'm using VMware's ESXi hypervisor, where I create 7 different virtual machines. So in total, they come to about 50 gig of RAM, 450 gig of hard drive, and I use 4 virtual CPUs on each host. You could also use something like Proxmox or KVM, or of course, if you have 7 physical machines laying around and they're networked together, you could use those too. The second requirement is a Red Hat account. That's free to sign up, and with that, you're going to get access to a 60-day trial license for OpenShift Container Platform, and also access to all the downloads that we need to get the cluster up and running. All right, so let's take a look at the architecture now.
Here we have the architecture diagram for the environment that we're going to be using throughout the video. You can see the environment is split up into 2 different networks. So we have the local area network at the top, and that should already exist. And then we have the OpenShift network at the bottom. And we're going to create that network in a moment using a port group in ESXi. This machine here is the local workstation. So in my case, that's just my Mac. You can see here that we've also got what I've labeled a helper node, and that helper node joins the 2 networks together. So you can see that it has 2 interfaces, one on the local network and another in the OpenShift network. Now the helper node runs a number of services that are required to spin up an OpenShift cluster. Firstly, we have a NAT gateway, and that's required because each node needs to be able to pull container images from the internet. So for example, this control plane node will come up and it will use the helper node as a gateway to get out to the internet and pull images. Now, in the case that you do not want to expose these nodes to the internet, you do have the option of setting up what's called a mirror registry here, and you can configure each of these nodes to pull directly from this registry, and you have alternate means to populate the registry, but we're not going to do that in this video. We're just going to stick to the internet. There's also a number of required DNS entries to ensure that all the nodes in the cluster can communicate with one another for a number of different reasons. We've got a DHCP service as well. This one is actually less important because you can provide each of the cluster machines with a static IP when you're booting them. However, I just find that it's easier to provide DHCP and static IPs from a single source of truth. We also have an Apache web server. This will host each of the configs and also the Red Hat CoreOS image that each of the hosts will actually pull during their boot process. We will also set up an HA proxy and load balancer for getting requests around the cluster and also into the cluster from external networks as well. So in this case, the HA proxy is not HA, but all of the OCP backend services that are proxies to are. And finally, we will also set up an NFS server, and that is so that we can host the OpenShift image registry. Now, each host machine, and actually the bootstrap machine as well for that matter, uses Red Hat Enterprise Linux CoreOS as the operating system. So there are some fairly big differences between Red Hat CoreOS and just regular Red Hat Enterprise Linux. First of all, CoreOS is an immutable container-focused version of Red Hat Enterprise Linux. CoreOS uses OS tree for versioning, like entire file systems. Basically, updates are delivered in a container as what's called like an atomic unit, and the new file system that is included in that is applied upon a reboot of the host. CoreOS also includes something called Ignition, which OCP uses as like a first boot system that can manipulate disks and configure the machine. And also CoreOS by default includes Kubelet and also the Creo container runtime engine, which now replaces Docker in version 4 of OCP. It is compulsory to run CoreOS for the control plane nodes. So these nodes here. These worker nodes, you do have the option of using Red Hat Enterprise Linux still, but just keep in mind that if you do choose to use Red Hat Enterprise Linux for these nodes, it can increase the management overhead of the cluster because you won't be able to take advantage of OCP managing the host OS upgrades for you. So in my opinion, it's best to stick to Red Hat CoreOS and only make changes to each of these hosts via the machine config operator once the cluster's up and running. So the general flow of the install is that we're going to use the helper node to generate the config files required for the deployment of OCP, and we're going to host them along with the Red Hat CoreOS image using the Apache web server. Then as a first step, we're going to boot the Bootstrap node. That will start first and pull in the Bootstrap ignition config from the web server, and it will also pull in the Red Hat CoreOS image to boot the OS. Once the Bootstrap machine starts, it will itself start hosting some resources that the control plane machines are going to use. We will then start up the control plane machines. These will also point to the web server so that they can get their ignition config, and they will also get a copy of the Red Hat CoreOS image to boot from. And then once they've booted, they will pull in whatever resources they need from the Bootstrap machine. The control plane nodes then together with the Bootstrap node work together to create a temporary Kubernetes control plane. This temp control plane, including the Bootstrap node that is, then schedules a permanent control plane to just the 3 control plane nodes. The Bootstrap machine then shuts down the temporary control plane, schedules some more workload to the permanent control plane, and is then ready to be shut down and removed itself. Finally, the worker nodes will then be started up, and with a little manual intervention with certificate signing requests, we'll get them joined into the cluster. I've created a repo with the instructions that I'll be using for this video, so I'll put the link in the description to the video, and we can get started creating the environment now. We can get started by downloading all the software that we need to boot the cluster. First of all, we need to download the latest image for CentOS 8. So you can come to this link here and you can select just this x86-64 ISO version of CentOS. I don't need to download it again because I already have. Next up, we can log into the Red Hat OpenShift Cluster Manager. If you don't already have an account for this, then you can create one as well to get access. Once it's loaded, you can select this Create Cluster button. Then we want to select Red Hat OpenShift Container Platform. From here, you have all the different type of infrastructure providers. So a lot of these ones up here will support the IPI method of installation. We want to select Run on Bare Metal. So once you get to this page, this has all the links that we need to download the software that we need. So the first piece of software that we need is the OpenShift installer. So we're going to run this installer on that helper node, and that helper node is the CentOS 8 machine. So we can select Linux and you can download the installer. I've already downloaded it. Also the pull secret, you want to download a copy of that. The command line interface, so these are the OC and the kube control tools. You can download that for whatever OS you're using as your workstation. So for me, that would be Mac. And you'll also need a Linux version of that as well for the CentOS 8 helper node. Then finally, download a copy of Red Hat Enterprise CoreOS. So if you open this, there's actually 2 files that we need here. One is the metal install, the raw.gz file, and we also need the one just above that, which is Red Hat CoreOS, the installer, but it's an ISO. So this is the one that we're going to boot inside ESXi. So once you download all of those assets, we can come to our virtual machine environment, ESXi, and we can first of all upload some of those files. So you can come here to the data browser, and I just upload things to an OS folder that I've created. So you want to upload the CentOS 8 image, and you also want to upload this Red Hat CoreOS, the ISO only. You don't need to upload the .raw.gz file. So just those 2 files. Once they've been uploaded, we can come into networking and we can create a new port group. So this will be the OpenShift. This will be for the OpenShift network, which was that network towards the bottom of the diagram. We can call it OCP and then just a random VLAN number that is not in use. The rest can stay default. We'll add that. We can now start to build the virtual machines that make up the cluster. If we come back to the GitHub repo, the specs for each of the machines are listed in this section here, prepare the bare metal environment. And you can see that we've got specs for the control plane nodes, the worker nodes, the bootstrap node, and also the services node. Now, these aren't the minimum required specs that the OpenShift documentation specifies. It's actually a little bit less, but that doesn't matter so much for testing environments. If you're looking for a production environment, you'll want to consult that documentation and follow those minimum requirements there. But what I'll do is I'll get started by explaining how I create one of the control plane nodes, and then I'll speed up the video creating the other control plane nodes, the worker node and the bootstrap node, and then I can slow it back down again and talk about this services machine that we build. So we come back to the ESXi dashboard, we select virtual machines, we create/register a VM, we can create a new virtual machine, select next. We can call this OCP-control plane-1. We select Linux, and it's a CoreOS machine because we're doing the control plane first. We can select next. I've only got one data store. Next. Now, according to the documentation, this here was 4 vCPUs. The memory was 8 gig. The hard disk, I'm going to thin provision and set that at 50 gig. We can remove the USB controller if you don't really want to keep that around. And then the network adapter here is going to connect to the OCP network. And then finally, the CD DVD drive is going to boot the Red Hat CoreOS ISO image, which is this one right here. Select next and finished. So we just need to repeat that now for the remaining nodes. For the OCP services machine, we're going to boot as a CentOS image. This machine actually does a little bit less than the other machines, so we can give it a little bit less RAM. I'm going to set that at 6 gig. But it does need a much larger hard drive space. And the reason for that is the services machine hosts the NFS server. And according to the requirements of the OpenShift image registry, which is backed by the NFS, which is backed by an NFS share, it needs at least 100 gigabytes of memory. So we're going to set this up to 150 gig. The other difference here is that we will be connecting to the VM network on adapter 1. And because this VM, this services VM, actually joins both networks together, we'll add an additional network adapter. And with this additional adapter, we'll join the OCP network. That way, with adapter 1, we're going to get a LAN IP address. And with adapter 2, we can set an OpenShift network IP address. And finally here, we're going to boot from the CentOS 8 image. Now that we've finished building the VMs, we need to collect the MAC addresses that are assigned to each one. Now, unfortunately, if you come into the network adapter settings of any of the hosts, you'll notice that the MAC address doesn't get assigned without actually starting the VM. So what we'll do is we'll start each of these VMs so that the MAC address can be assigned, and then we'll take note of them. We can actually immediately shut everything off except for the services node because we'll be using that first. And now you can see if we go into the control plane 1 and we have a look at the network adapter, we can see that it now has a network address, a MAC address assigned. So I'm going to take note of these MAC addresses because we'll use those when we're assigning static IP addresses. We can now continue by installing and configuring the OCP services machine. Select your preferred language. And time and date. So I'm going to select server-based environment, and I'm going to select the guest agents so that the VMs resource statistics show up in the ESXi dashboard. I will also configure the installation destination. So what I'll do is I'll select custom and then done, and then click here to create them automatically. You can see here that it's actually using 92.47 gigabytes for the home directory. I don't want that, so just going to remove the home directory, and you can see that the root directory is currently configured with 50 gigabytes. If we just clear that out, it will use all remaining disk space just for the root directory. We can then click network, and you can see that we have the two network devices that we created. The first network is part of the LAN. So if we turn that on, we should get a DHCP address. That's good. So we can see here that we have an IP address of 192.168.0.96. And the second is on the OCP network. So you'll see if we turn this on, nothing's going to happen because we don't have any DHCP based service running at the moment. So that'll actually be what this host is for. So we can turn that off for now. We can assign the host name, and we can begin the installation. We can now remove the CD-ROM from the machine and reboot. Once we get the login prompt, we can have a look and see that we still have that network assigned. So we can see 192.168.0.96, so that's the IP that's assigned to this host. So what I'm going to do is just SSH into that machine to make this a little bit easier. Okay, great. So we're able to SSH into the machine. That's a good start. Now what we need to do is move all of the files that we've downloaded before onto this machine. So we just want to do an SCP, and I have everything still in my downloads. So we want to move the OpenShift install for Linux. We also want to move the OpenShift client and also the Red Hat CoreOS installer. And in this case, we want to get the raw.gz file. We're going to send that to root, and we can just do it in the user's home directory. So we can see we have all these files here now. So what we want to do next is we want to extract the clients. That gives us OC and kube control, and we can move them to the user local bin directory. Now we should be able to kube control version, where we can see the version and OC version as well. So we have the client tools working. We also want to extract the installer. And you can see we now have this OpenShift install application. We need to update the operating system so that any new packages that we install now will get the latest versions. Next up, we will install Git so that we can clone the repository with all the configuration files in it. Okay, let's clone that repo. And there we go. We have the OCP for Metal install. Just to have a quick look in this. You can see we've got DHCPD configuration. We've got the diagram that we've talked about. We've got some DNS configuration, the HA proxy as well, the install config that's fed to the OpenShift install, some manifest files that we're going to configure OpenShift with once we have it up and installed, and the README is the instructions for this. Now, the next step is optional. I just prefer to do it because I think it makes editing YAML files and just using Vim a lot easier. We're just going to turn syntax on, then we're going to set number. We're also going to have expand tabs and auto indent set, tab stop to 0, tab stop to 2, shift width to 2. List is very helpful for YAML files because it will show you where you have tabs and where you have spaces, and then HLS is to highlight search. So we'll save that. And we're just also going to update our preferred editor to Vim for each of the tools OC and kubectl. So now we have to set the static IP for the OpenShift network interface on this host. So what we can do is we can use the network manager text UI, and we can edit the ENS224 interface, which is our second interface. And we can update the IPv4 configuration by coming down to automatic, changing that to manual, select show. We can add our address in here, 192.168.22.1. So if we come back to the diagram quickly, we can see that we're setting up this interface here, interface 2. We can change the DNS server to localhost. At the moment, we do not have the DNS server up and running, but we'll get to that in the next step. And we can also update the search domain. So the domain we're using for this network is ocp.lan. Never use this network for the default route, and also automatically connect. Okay, so now that we've done that, we want to confirm that that has taken effect. So we can see here ENS224 now has that IP address. If it doesn't, you can bounce the NIC. And now we can set up the firewall. So firstly, we want to set up these zones. So we've got an internal zone and we've got an external zone. So to do that, we can run the network manager CLI. We should now be able to query our active zones. So you can see that in that list, we have the external and the internal. We can also check the active zones. And we can see that we have external and internal are active, and they're assigned to the correct NICs. Next up, we have to set masquerading on both zones. So masquerading is basically source NAT. And to give a quick example of what that means, it means for every packet leaving the external interface, which in this case is ENS192, after those packets have been routed, they'll have their source address altered to the interface address of ENS192. And that way, any packets that go outside of the network will be able to find their way back to that interface where the reverse will happen, and the packet will be passed on to the correct host. Again, we can use the firewall command to do that. And we can reload the firewall config again. We can check that those changes have taken effect. So we have masquerading turned on both interfaces. Now we want to make sure that IP forward is also configured. I believe when you enable masquerading in CentOS 8, it automatically enables it by default, but we can check this and we can see that that's enabled. Next, we can install DNS. We can now apply the config that was included in that Git repo that we cloned earlier. I'll just quickly go through that first though. If you navigate into the DNS directory, in this directory, we've got the named.conf, which is the primary configuration file that points to the zones. That's mostly default settings. You can see everything up the top is basically just a default configuration. The only differences are that Google DNS is put in here, and then also a link to the zone files that we're also including. In the zones directory, we have the forward and reverse lookup. Here you can see we've just assigned A records to a lot of the machines that we're using. Because the services node will also host the HA proxy, we've pointed the OpenShift required DNS addresses to that proxy. And importantly, we also have these service records down here for the etcd cluster. So when the etcd cluster is booting, it can find out how to contact each other. I've left these two entries in here down the bottom because later on, these will be required in the LAN network. So we're going to add them to the hosts file of the workstation that we're working on, but you could also configure DNS in that network as well. So you'd have to take those two entries and also this wildcard entry here and put that into another DNS. We can take a quick look now at the reverse record as well. And again, we just have a number of pointer records in this case that are also required by OpenShift. And all these records are in the OpenShift documentation as well. We can apply this configuration now by copying it over from the Git repository to the server's configuration. Once again, we can reload the firewall for the config to take effect. And we can enable and start the DNS service. And there we go, DNS is up and running. So let's do a quick test and look up the details for the domain that we're using, the ocp.lan domain. You can see here that this host is not using the correct DNS server, the DNS server that we just set up. It's still using the DNS server from the LAN address. So you can see down here, the server that it's queried is 192.168.0.1, which is the LAN network. So we want to change that now. We can do that by updating the external NIC, the ENS192 NIC on the LAN network to automatically ignore any DNS entries that have been obtained via DHCP, and also to point to the local host for any DNS queries. We can then restart Network Manager, so that takes effect. We can see the machine is now using localhost for DNS queries. We can do a reverse lookup test that should resolve to the OCP bootstrap machine, for example. Great, so you can see here that we've resolved that host name. Now it's time to install and configure DHCP so that each of our servers get a static IP when they boot. And again, we have a template that we require for the configuration of the DHCP server, except this one here we will have to update with the MAC addresses that we got from the ESXi console earlier. Once we've completed that, we can save the config and apply it. We can then update the firewall to allow DHCP on the internal zone. And then we'll need to enable and start the DHCP service. And the service is up and running. You can safely ignore this warning message here because we're not providing DHCP on the ENS192 interface, that's the LAN interface. Next up, we can install and configure the Apache web server. By default, Apache listens on port 80, but we'll be proxying traffic for port 80 and 443 using Nginx. So we're going to update the port that Apache listens on to port 8080. Once again, we can update the firewall to allow access to port 8080 on the internal zone. And we can enable and start the service. Here we can see that we have Apache running on port 8080, but we can always do a quick test with curl as well. This just prints out the HTML of the default Apache web page. Okay, two more services to go. We have HA Proxy and the NFS server left. So let's do HA Proxy first. We can install that. Before we copy over the config, we'll take a quick look at it. The top of the config is mostly just defaults. We then come down the page and we can see that the HA Proxy stats is enabled. So that's at the URI of /stats and the port 9000. So this is not a requirement of OpenShift, but I think it helps when you are doing the install. You can see each of the front end and back end services light up green as the hosts come online. We then have the front end and back end configuration for the Kube API server. So everything coming in to this host here on port 6443 will be at first proxied to each of the control plane nodes as well as the bootstrap node. So later we'll come through and we'll remove that bootstrap node. Moving down, we have the front end and back end for the machine config server. So this is for each of the hosts to pull their machine config that they boot against. And finally, at the bottom of the config, we have the HTTP and HTTPS front end and back end configured to point to the worker nodes. These are just running at the layer 4 TCP mode. The reason that we're not doing this with layer 7 HTTP is because we just want to pass through the connection to the worker node and let the ingress controller decide what to do at the HTTP layer. So let's copy that config over. Now, obviously, HA proxy is listening on a lot of ports here, so we have quite a few firewall rules to add. So I'm just going to copy and paste the firewall rule block. Now, before we enable and start the HA proxy service, we just want to quickly set an SE Linux Boolean value as well. And then we can enable and start the service. And finally, we need to install NFS and configure a share. If we have a look at our disk, we can see that we have 139 gig free on the root file system, which is where we will be making our share. So we can make that share now. And then we want to export the share. We can check that that worked. You can see we're now exporting the shares/registry directory to any host on the 192.168.22 network. And again, we can set some firewall rules for this service. So if you're following along with the GitHub repo, there's a block of firewall rule commands that we can paste. And then finally, we can enable and start the service. Okay, so we've finally reached the end of setting up the environmental services. Now we can get on to actually generating and hosting the install config so that we can boot the OpenShift cluster. So the first thing we need to do is generate an SSH key pair that will be used to authenticate to each of the nodes in the OpenShift cluster. We can leave everything as default. CoreOS doesn't provide a default password for the core user, so this will be the only way to authenticate against those servers. Next, we want to create an install directory where all of our install files will be held. We can then copy the install config YAML file that's included in the GitHub repo into this new directory. We then need to update the install config YAML file with a couple of pieces of our own private information. On line 23, we need to enter the pull secret that we got from the Red Hat Cluster Manager site. And then on line 24, we need to enter the public SSH key that we just generated. And then we can save that file. We're now going to generate some install files that will take in that install config file, and it's destructive. So if you want to take a copy of the install config file and just move it to somewhere temporary, you can do that now. First, we're going to generate the Kubernetes manifest files. We do that using the OpenShift install command. You can see here that it gives you a warning that it's making the control plane schedulable by setting the master schedule to true. If you want to run workloads on your master nodes, you can leave it as is. If you don't want to run workloads, we can actually change that now. We do that by updating the OCP install manifests cluster scheduler o2 config file, and we can alter the master's scheduler value from true to false and save that. Next up, we generate the ignition configs that will be used by the bootstrap, the masters, and the worker, and we also generate the Kubernetes auth files as well. So again, we're going to use the OpenShift install command, and we will point it to the OCP install directory again. And you can see that we now have in the install directory an auth directory, as well as the bootstrap master and worker ignition files, and then also a metadata file that goes along with those. Now what we need to do is create a directory that Apache will use to host these files so that each of the VMs can pull them when they're booting. We can just call that directory OCP4. And we're just going to copy everything that's in that OCP install directory into this new OCP4 directory. We also need to move the Red Hat CoreOS raw image that we uploaded to the server at the beginning of this server setup. It's a good idea that when we're moving the file, we rename it to something shorter just because we're going to be typing it a few times soon. We can change ownership of all the files inside the OCP4 directory to Apache so that they're not owned by the root user. We can also modify the permissions of all the files in that directory. And because we're using SE Linux, we can also change the context type of all the files in that directory as well. To confirm everything looks good, we can do a quick curl test. And here we can see that we have the auth directory, we have the bootstrap ignition, the master ignition, metadata.json file, Red Hat CoreOS image, and the worker ignition as well. So that's everything that we need. We can now look to use these files when we deploy the OpenShift nodes. To do that, we can navigate back to the ESXi console. We can start with the bootstrap node. So we power the machine on and it loads CoreOS. We can hit the tab key and that will bring up the boot options. These boot options will mostly be the same for all of the machines except for the ignition URL that will point to obviously a different ignition file depending on the type of node that it is. So here we can see that we set the install device to SDA. That will be the same for all nodes. We set the image URL to the Apache web server, and then we navigate into the OCP4 directory and point out the Red Hat CoreOS raw GZ file. That will be the same for all of the nodes. And then finally, we have an additional setting for ignition URL that also points to the Apache web server. And depending on the type of node, you would specify bootstrap.ign, master.ign, or worker.ign. So we can also set up the control plane nodes as well now. So here you can see that the only difference is that the ignition URL is now pointing to the master.ign file. So we repeat that config for all three of the control plane nodes. And then we can start these up. So we start with the bootstrap machine first. You can see here that it will start to pull down the image, and then it will install the image as the OS using ignition to boot the host. We can do the same with the control plane nodes now. We can also monitor this via a command that we can run on the services node. So here I've specified debug, but there's also the options of error and info. While we're waiting for some feedback here, we can also go and start the worker nodes as well. And we can start those. You can see we're now waiting up to 40 minutes for bootstrapping to complete. Now is also a good time to bring up the HA proxy stats page so that we can watch some of the front ends and back ends turn from red to green. There isn't really a strict order to any of this because all the different components just wait for their dependencies to load. You can start the machines in a different order. However, if the dependencies aren't met by the time a timeout is reached, then you can have issues with installing. If you get bored, you can also SSH into any of the nodes and watch as the containers come up and go away as their tasks finish. Now we can see that the bootstrap has completed. It took a total time of 19 minutes and 21 seconds. We can see with the HA proxy stats page that the control plane nodes are now all up and the bootstrap node is now red. The info message in the terminal says that the bootstrap node is now safe to remove. So what we can do is we can come back to our services machine, and we can update the HA proxy config to remove that bootstrap node from the backend services. And then we can restart the service. We should now see the bootstrap machine removed from the stats page. We can now listen for the install complete event, again using the OpenShift install command. So because we said that the master nodes were not schedulable when we were building the configuration, we need to bring the workers up for the installation to complete. This is because the OpenShift router will be deployed to the workers, and there's some cluster operators that rely on that router to come up, like the authentication and the console operators. So once the worker nodes load, the router can load, and therefore all the cluster operators can load successfully. So what we can do is we can leave this command running, and we can make another connection to the OCP services host, and we can join those worker nodes in. So first what we want to do is we want to export our kubeconfig environment variable that points to our kubeconfig. Once we've done that, we can test that we can access the control plane. You can see here that we're able to authenticate as the system admin user. Now we need to take a look at the certificate signing requests that have come from each of the nodes. So you can see that we've already got 2 pending requests. I'm going to copy a command that approves all pending requests. You can see that has approved 2 CSRs. We just need to keep an eye on some more coming in. And there we go, we have worker 1 as well. So we can run that same command again to approve those. And we can keep an eye on the HA proxy stats page. We can also run OC get nodes. We can see that the cluster now knows about the worker nodes. They're not ready yet though. So as long as all these CSR requests have been approved, the cluster should continue to install successfully. We can come back and we can wait for our install complete command to finish. Okay, so that's all green now, which is good. While we're waiting for that to complete, we can actually configure the storage for the image registry. So if we come back to our other connection, we can have a look at our cluster operators. We can see that the console and the authentication operator are still unavailable. Here it says that the image registry is available, but that will change. So what we can do is we can just update the storage now regardless. What we want to do here is update the management state. You can see here it's been removed. So we want to change that to managed. And we also want to update the storage section. At the moment, it's an empty object. This is where the BIMRC configurations that I pointed out at the start of the video would help. But I didn't save that to the bash profile, so it's not taking effect right now. So we just want to add an empty claim here. And then we can save. So that should create us a PVC. You can see we now have a PVC that's in a pending state. That was created 19 seconds ago. So what we want to do now is actually create a persistent volume so that this PVC can bind to it. We have the manifest for that available in the GitHub repo that we downloaded earlier. You can see here it's a pretty standard NFS persistent volume with the access mode read write many specified and 100 gigabytes of space. We can have a quick look at the image registry storage PVC as well and just confirm that that will match up. So we can see that that's requesting the access mode of read write many and also storage of 100 gigabytes. So that should be fine. We can then create that persistent volume. And we can see that that is now bound. We can also see that all the cluster operators are now up and running. So we can come back to our install complete command. Still looks like it hasn't finished. Okay, I'm not sure why that hasn't finished, so we'll give that another minute and just create the first admin user while we're still waiting. Otherwise, I think we can ignore that because all the cluster operators are up and running anyway. Oh, there we go. All right, great. So that's complete now. We can see that the installation was successful. A couple of things to note from this output. Just remember to export the kube config each time you come into the server if you haven't added it to your user's bash profile. We can also take note of the console address here. So I'll just copy that, take a note of that. And also we want to take note of the kube admin user's password. We'll need that in a moment as well. Now, if you don't have this output for some reason, don't worry about the password too much. There's another way that you can get that. It's in the auth directory that when we originally created the configuration files for the cluster. You can see it's under the kube admin password. So we don't really want to use the kube admin credential all the time. So it's a good idea now to create the first admin user. So I've actually supplied the manifest for that as well in the repo. So we can have a quick look at that. You can see this YAML file actually has two manifests in it. The first is just creating a secret, and the content of that secret is an HT password field. So you can see I've got a note in there that I've used HT password with the username admin and the password. So if you want to substitute that, you can just substitute that text. And then down the bottom, we have an OAuth config that just maps that HT password secret to the OAuth provider. So we can apply that now. We can safely ignore those warnings. We now have an admin user that's been created. So we now need to give that admin user cluster admin permissions. Okay, and that admin user will exist when we log in. So now we can finally access the OpenShift console as the very last step. So ideally, we'd like to do that from our local workstation. So to get that set up, we have to add an entry to our ESXi host directory. And we just want to paste in an entry that I've included on the README in the GitHub repo. So basically what this is saying is any of these DNS names that we attempt to navigate to are going to be directed to the 192.168.0.96 host. And we know that that's our OCP services machine. So once it hits that, it will then hit the HA proxy, which will then transfer the request to the appropriate endpoint. Now, ESXi host doesn't let you use a wildcard address. Otherwise, we could just have star.apps.lab.ocp.lan. So if you don't want to be adding a new entry in this file here for every new service that you create on the cluster, you can sort out DNS. Perhaps you can use the DNS server that we've just created on the OCP services machine to also serve DNS to your local workstation as well. But for now, this is an easy way to get up and running. So we can save this. We can get that URL again. We can come back to Chrome and we can navigate to the console address now. And now we have the option of logging in directly as the kube admin user, or we can also use the OAuth provider where we configured the HT password access. So we'll choose the HT password. We can enter admin and password. And there you go, a fully functioning HA OpenShift cluster, and all green ticks means it's a healthy cluster.
And there we have it, OCP running in a bare metal environment. Now you're going to want to leave the cluster running for at least 24 hours because the first certificate rotation happens in the first day. Once that completes, you're free to shut the cluster down and bring it up whenever you like. Just remember, shut the worker nodes down first, then the control plane, and then you can shut the proxy down. When you're bringing it back up again, do that in reverse. Bring the proxy up, then the control plane, and then the worker nodes. So go enjoy, build, and run all your containerized workloads. And if you enjoyed the content, please leave a like and stay tuned for more videos coming soon. Thanks, bye.